start the record on this thing. And you can minimize that GoToMeeting screen. Up next to the X, there's two arrows that touch. If you click that, it kind of minimizes so that it doesn't take up so much of your picture.
Okay.
And what I have here is a drawing tablet where whatever I write on the tablet, you should see.
Yeah.
All right. Your mom thought you had some pictures that you wanted to go over, some graphs or something. You want to go?
Yeah.
Let's learn how to do this.
Okay.
It doesn't take. It's actually amazingly quick. Go ahead and take at least one. Don't take too many and send it all together because it slows it down. But take
Right.
at least one picture and send it to my email as a large file.
I gotta grab my
Okay.
binder real fast.
Okay. And the only thing about taking pictures is make sure you have good light.
Alright.
Okay, either use the flash or just put a lamp over it so it's got decent light. It needs pretty good light.
So what's your phone number?
Don't send it to my phone.
Oh, okay.
Send it to this email address that you see up there. Hold on a second. What happened to it? There it is. Let me expand.
Oh, okay.
Because if you send it to my phone, then I got to send it to from my phone to my computer. So if you send it directly to my email, then I can pull it up and we'll both be looking at it.
Should I email you the messages? Or
No,
make it like
picture. Take a picture, and
okay.
when you're looking at that picture, share it. And
Right.
when it asks to share it with who, choose Gmail or my email address that you're looking at there.
Okay.
And once you type my email address one time into your phone, then the next time you go to send a picture, all you have to do is type the first two letters and it'll show you the whole thing. So it's not like you have to do this very often. Type it in the full email address. If you hold the camera about 12 inches above the piece of paper, that generally, you want everything on the paper in the photo, especially if you have an Apple, the resolution will be great. We'll be able to see everything in detail. Tell me after you've sent it.
I just sent it.
Okay. Sometimes it takes a half a minute or so for me to receive it. Ah, there it is. All right. Let me zoom in a little bit on this. Is there one in particular you want to start with, or?
No.
This is matching the function with the graph.
Yeah.
Where's the top of the, hold on. Oh, okay, I got it now. So you just want to start with 31?
Sure.
31 is what kind of a function and what kind of a graph?
It's a parabola.
Okay.
And it looks like it's moved one to the left.
It's actually in vertex format.
Right.
Okay, so the vertex you're staring at, the vertex is where?
At -1, 4, or -4.
-1, -4.
Right.
So we have to, and the parabola faces up or down?
The parabola faces up.
Okay, so there's one right there, number J. Notice that the vertex is at -1, -4, and it faces up. Okay. 32, what is that?
Also a parabola in vertex form.
The vertex is where?
It's at 3, 2, or 3, -2.
It's 3, -2. In other words, here's the standard format for a parabola. It's always, before calculus, it's always minus h and minus k. The reason this is a plus k is because it started out on the other side of the equation where it was y minus k. Notice all of your conic sections are x minus h and y minus k. Okay? So if this is the general form, then h in this case is a +3 and k is a -2. Which way does this parabola open?
Open, so it would
Up or
open.
down?
It opens down.
Because of the negative sign, right.
Right.
So which graph are we looking at that has a vertex at 3, -2, and opens down?
Would it be B?
Uh-huh. Okay, we can go through these pretty quick. What's the vertex on 33?
-1, -4.
-1, +4. Now,
Oh.
I know I spent a lot of time telling you it was always minus h and minus k, but like I said, this k is positive because it started out as y minus k. And they moved it to the right side, and that's how it turns positive.
Right.
Okay? But this is, you definitely need to memorize this general format, because then you'll be able to figure out what the vertex is. So the vertex is where?
At -1, +4.
Okay.
Or no, negative.
And
Positive.
up or down?
It would be facing down.
Which letter?
So, -1, H.
Correct. Let's skip around. We're only doing a half an hour tonight. Let's make sure we cover some of these others. I do like the way they give you 4 examples for each. But let's jump to 35. I think you got 34 down.
Right.
35 is the square root function with what translation?
So it's flipped
Over which axis?
over the x-axis,
Uh-huh.
and it's moved 2 to the left.
Correct. And this is what it looks like normally.
Right.
Okay, so you do the flipping first. Move it 2 to the left, looking for something like that.
O. The answer.
Yep. Okay. How about 36? This is an interesting one, 36. Let's write it out. We have y equals the square root of 4 minus 2x plus the 1. I'm sure you know what the 1 does.
Moves it up.
Correct. But the inside is a little different than we're used to. In other words, notice that it's got the number here minus the 2x. Well, I could handle that easy enough by writing it like this. But now what's the consequences of that negative sign? We're not clear. In other words, normally that would be a flip over the y-axis, right?
Well, wouldn't it make it impossible or
No.
exist?
No, not at all, because it's a negative number.
Yeah, because if it's more than...
It's not a negative number. In other words, x is going to have to probably be negative. But here's what I'm getting at. In other words, for it to be a flip over the y-axis, it has to be f of minus x. Okay? Well, notice that when I wrote it like that, it was not f of minus x. You need the minus sign to be in front of everything that is under that square root thing. Okay? So if I examine, this has 4 things happening. That is what?
Flip over the x-axis.
Over the y-axis.
Of the y.
If I wanted to flip over the x-axis, I'd put the negative sign in front of the radical.
Okay.
Because here's the difference. If minus f of x, that's a flip over the x-axis. But f of minus x is a flip over the y-axis.
Okay.
Now, this still has a bunch of other stuff going on. But the very first thing is the flip over the y-axis. You'll always do your reflections first. What's the consequence of the 4? The minus 4.
4 to the right.
Correct. And what's the consequence of the 2?
Makes it grow by 2.
And that's a horizontal compression.
Horizontal compression.
And the same reasoning. In other words, if I said 2 times f of x, that would be a vertical stretch factor. But if I say f of 2x, that's a horizontal compression factor.
Okay.
Okay. So, we have a horizontal compression by a factor of 2, which is going to be difficult to see. We have a translation to the right of 4 units after we've flipped it over the y-axis. Then we have a vertical shift up 1. So let's find that curve. Let's see, right offhand, in other words, let me draw the normal curve again. The normal curve is this. So if I flip it over the y-axis, it's going to look a little like f. And if I shift it, now f is shifted 2 units. Ooh, this is... hold on a moment. F is actually the curve. And I didn't write it properly. And first of all, let's figure out how I know that that's true. Okay? Notice that when x is 2, y needs to be 1. Right? Well, when x is 2, the inside is 0, and y is 1. So it's not a translation of 4 units to the right. That's because I didn't write it correctly. This is always the trickiest part of this. You need to write it like this. Notice that that's the same thing we started with, right?
Yeah.
But now, if I was writing this in f of x notation, I could write it as f of minus 2 x minus 2. And now, there's my reflection over the y-axis, there's my compression factor, and there's my horizontal translation. So figuring out how to write it when it's inside the radical and the x has a negative sign is always a bit tricky. But I figured out that it had to be like this because I can tell from up here that when x is 2, the radical is 0 and I have just 1. And that's that picture right there. So I know the shift was not 4 units. The shift had to be 2 units. And exactly 2 units to the right. And F is the only thing on there that even comes close to fitting that picture. I think. Let me...
F and T.
Ah, F and T. Ah, what's the difference between F and T?
Horizontal compression.
Yeah, horizontal compression factor. Well, which one are we looking at?
F.
F, exactly. In other words, it compresses it horizontally, which is going to make it look more like this and less like T. Okay. There must be another one in this same row that is going to be T.
I think it's 37.
Yeah, and let's figure out how to write 37. Because that's the only hard part of any of these, is figuring out how to write it as you would as an f of x. Notice that this is kind of similar. 8 minus 4x. We have a negative sign in front of the 4. So how should I write this properly so that I'll know the exact translation?
So you want to take negative 4 x minus 2.
Exactly. And now we're looking at the same thing. We have, in other words, if I write it in f of x notation instead of y, it's f of negative 4x minus 2. That's how I would write that. If I told you that f of x was square root of x, well, what is this? This is it. Plus 1. Plus 1. And this, this has a compression factor of 4. What does that tell me?
It's going to be horizontally compressed more.
More, which means this 37 has to be F, and 36 is T. Now, if I wasn't completely sure, I can certainly fill in a point. I can tell that when x is 0 on F, when x is 0, y is 4. Whereas on T, yeah, that's not true. So let's see. When x is 0, what is y?
When F is 0.
When x is 0. In other words, if I look at the F chart, I can see where x is 0 and y is 4.
So it'd be square root of 8 plus 1.
How is that 4? Yeah. Ah, 38. No, absolute values always have this corner in them. Interesting. 37. Square root of 8 plus 1 is not 4.
Or it might not be exactly 4.
Well, over here, 36 is when x is 0, we have the square root of 4, which is 2 plus 1, so this should be 3 when x is 0. So 36 is not f. Let me look at t again. When x is 0, y is 3. That's 36. 36 is t.
The square root of 8 plus 1 is 3.8.
Right. That's, so far, we haven't found that curve yet.
Oh, okay.
We haven't found 37 yet. 36 is t. And this is more than just seeing the shape. In other words, when we have two shapes that look pretty similar, like f and t, then we have to check a point. The point I checked was when x was 0. Well, over here, y is 3, and up here, y is 4. Well, the only one that y is 3 is 36. When I plug 0 in for x, that ends up being 3. So that has to be t. No, yeah, no, that does. That's a reflection over the y-axis also. Now, 37 must be on there also. We just haven't seen it. 37, is there another one on here that goes that way?
Mm-mm.
Let's see it. Is there a graph for every function?
Yeah.
I only see 2 square root functions, but there's a lot of log functions. Well, let's go on. Let's not get hung up on that. There's something wrong. I'm not sure what it is, to be honest, because it seems like f, well, I know that 36 is t. 37 is a greater compression factor, so you would think that 37 would have to be f, right?
Mm-hmm.
It just doesn't pass my point test. In other words, when I plug in 0 for x, I got the square root of 8, which is definitely not 3. It's close.
Right.
It's close. Maybe that doesn't actually go through 4. Maybe that goes through like 3.8. In which case 37 would be f. All right. 38. Let's have a look at. I can figure out how to get that stupid image off. You're not going to be able to help me because you got... All right, there's 38. So let's write it first of all. So here's our elementary function, which looks like this. What's happening on 38?
It's a horizontal compression by factor.
Start with the reflection, because you always want to do your reflections first.
Oh, it's flipped over the x-axis, horizontal compression of a factor of 2, moved 1 to the right, and up 3.
Right offhand, that looks like number D. But notice one thing. I have to write this slightly different also. I'm going to write it like this. See the difference?
Oh, okay.
Now what is the translation? The horizontal shift.
Half to the right.
Only a half, exactly. In other words, you always kind of have to set them up like this. This is very similar to what I did on the square root functions also. I factored out a 2 so that I would have my x minus h. That's x minus h right there. There's the horizontal compression factor. and 3 is the vertical shift up by 3. So it certainly looks like D.
Mm-hmm.
And I suppose that it's always worth plugging a point in. What should this be when x is 0?
So, point. 2 minus 1 negative. So it'd be -2?
No. Plug in 0 for x. What now is inside the absolute value signs?
-1.
What's the absolute value of -1?
1.
And then put a negative in front of it because this negative is outside. So that's -1 plus 3.
So it'd be 2.
So it's 2, and that matches this graph right here. And now we're sure that we have the horizontal compression properly. In other words, once you find a point and it matches, now you're done pretty much. That really is the last step, and an important one, I think. All right, let's look at 39. 39 is a bit easier. What's the first thing happening in 39?
So it's flipped over the x-axis.
Okay, and then next?
And then it's moved right 2 and up 3.
Okay, so let's find that.
So it's W.
Yeah, moved right 2, up 3, and flipped. Notice that it matters. If you move it up and then flip it, you don't get the same curve as if you flip it first. So you always have to do all of your reflections first. All right, number Y. Boy, they gave you some toughies. I don't know why that surprises me. Of course they are. They're not going to give you the easy ones. It's 7 o'clock. Did you only want to just do a half-hour session tonight?
I don't care. We can go on.
You want to just do the whole full hour and go through the rest of these?
Sure.
Okay, let's do it. I want to do at least a half hour just so you could realize how this thing works.
Yeah.
I think you're seeing now that it works pretty good. I mean, I don't know. Do you see any loss at all?
No, I like it.
In fact, there's gain. I'm recording this session. You're going to get to see how to redo some of these tougher problems.
Okay.
Okay. So 40 is greatest integer function of 1/2 x plus 2. Am I going to write it like that?
No.
How am I going to write it?
So make the...
Factor out the 1/2. That's all. That's what you're doing. Is factoring out the 1/2. What's left behind?
Oh, x plus 1.
Okay. Now that's the same thing. So now we're looking at the greatest integer factor. That's what? What's the 1/2 do?
It
Compresses or stretches?
stretches.
Correct, by a factor of 2. What's the plus 1 do?
The plus 1 moves it up 1.
No, that's inside
Or
the...
down 1.
No, has to be a horizontal.
Oh.
What I'm really looking at here is this.
Right.
Well, since it's supposed to be x minus h, h must be -1.
Mm-hmm.
So if h is -1, it's horizontally shifted left. And then finally this -1 is what?
down 1.
Okay. Now let me just draw the basic function. All I need, I think, is 2 points. So we're looking for a stretch by a factor of 2, a shift left 1, and a shift down 1. Well, G, right off the get-go, has the stretch factor by a factor of 2. It's also shifted 1 to the left, but not down 1. Now, on this greatest integer function, a shift to the left looks exactly the same as a shift up. Notice that if I were to take my standard and move everything to the left, no, it doesn't look.
Right.
It doesn't look exactly the same, does it? No, it would look a little different. Let's see, how many greatest integer functions are on this thing? We
2.
know, yeah, and it just 2 of them.
Mm-hmm.
Yeah, no, there's another one over here, bottom left.
Oh.
But that is highly compressed, not stretched. So that's not one of them. Does it just go through X? Yeah.
And G is flipped, so it has to be N.
Well, when you say G is flipped, what do you mean? The open arrow is to the right, so it's not flipped over the Y.
The function is negative, but it's decreasing.
Ah. So it has to be N. Yeah, you're right. Now plug in a point for X and let's see. Plug in 0 for X.
So 0 plus 2, so greatest integer of 2 minus 1.
So it should be 1, and that is 1 right there. Can you see where my cursor points?
Yeah.
That's X equals 0, Y equals 1.
Okay.
Okay, all right. Let's scroll up. So this is going to be a flip over which axis? G.
Mm-hmm.
Which axis is that a flip over?
The y-axis.
No, the X.
The x-axis.
Because that would make it go down instead of up.
Mm-hmm.
If you flip over the y-axis, then the open circle goes to the left side of that thing, and the closed circle is on the right. Or in this case, just the open circle. So you know that if it flips over the y-axis, it's going to look very different. All right, let's see. Let's look at 41. Tell me how to write it. Here, I'll write it the way it's given.
So you want to take the 2 out so that it's greatest integer of 2, x plus 1, and then minus 1, and then it's u.
So now we still have, now we have, what's the 2 do?
The 2 compresses it.
Correct, which means the width of each leg is only going to be a half a unit. Well, I remember seeing that down there on the lower left. Each leg is a half a unit. So pretty much has to be that. Plug in a point, make sure. And you don't have to pick 0, but it's usually the easiest math, an x of 0. So what do you get when you plug in x of 0, Dawson?
So it'd be 2 minus 1 again.
Again, and that's exactly where that is.
Right.
The only question here is what the heck are these two things?
Yeah.
That's a typo. Those are the ends of those two next steps.
Yeah.
All right. Let's look at some of these other. 42. There's only one left, isn't there?
Yeah.
Which one does 42 have to be?
G.
Okay. Before we answer that, plug in a point.
So 0 minus 1 equals -1 at 0.
Right there.
Okay.
Okay. 43. Now these become much easier. It's a consequence of the negative sign.
So it flips the function.
Over which axis? There's two ways.
Yeah.
There's two ways to flip. You can flip over the x-axis or the y-axis.
So it flips over the x-axis.
Okay. What's the 2 do?
The 2 makes the amplitude.
No. Amplitude is in front. Let's talk about the sinusoid function. Why they call it something different, I don't know, because here's what it is. A is the amplitude. In other words, you need a number in front of the sign for it to be an amplitude change.
Okay.
B is, in this case, the 2. And the +3 is the D. So we know the whole sine curve has been moved up 3. Well, which one are we looking at that looks like that might be the case?
B, L?
Not L, and I'll tell you why. Here's, if you start with the sine function, and you flip it, what you get is this. So whatever we're going to look at, if it hasn't been laterally shifted, it's going to look like my blue line. But if I look at L, notice that at x equals 0, it's starting right there at 3. Well, plug in x equals 0 here.
So
it is.
So x?
So 43. So when x is 0, sine of 0 is 0. It should be at 3. How many other sine curves are on here? Just one. This one here. Now see, this one here is doing what my blue line says. Right? And notice that the point 0 was a bad point to choose accidentally because it produces a y value of 3 in both of these charts. So it is important to know that if we flipped it over the x-axis, then the start is you go down, not up at the beginning. Well, if you look at this one, that starts by going down and then up. So this curve right here is negative sine x plus 3, or if it's compressed or expanded, negative sine 2x plus 3. The 2 is just a vertical compression, and that's hard to see on that picture. I mean, you know the period of sine is 2 pi, right? So from this point to that point should be over 6. If pi is 3.14, but since it's been horizontally compressed, that's only about 3.14, which is where it should be. X is definitely the curve.
Okay.
Okay? But again, the biggest, hold on. All right. The biggest clue was the negative in front of the function, meaning it had to be flipped, meaning it had to start down and not up. Now, 44 looks very similar, and in fact is exactly the same except for one thing. What is the one thing different?
It's half, not 2.
Is it compressed or stretched?
Stretch.
So it's stretched over 43. So we're looking for something that looks just like X, only is
I.
There you go. Notice that on I, when X is 0, it's still 3, but it starts by going down. That's the key. A normal sine function starts by going up and then down. This one goes down and then up, and it definitely has been stretched out horizontally like an accordion. Okay. Cosine curve, 45. How many cosine curves do we have on here? We haven't seen so far. None on the bottom row. None, none, none.
Well, it has to be L, doesn't it?
Ah, yeah, sorry. Now notice Y. That looks like a sine curve, but a cosine curve looks very similar. In other words, if I draw a cosine curve over here, looks like this. Starts down, comes back up. But if, and that's not what L does, but there's also a horizontal shift in 45. Notice that if I were to shift this thing a little bit, I could easily make it start down at the origin and then come back up. So it's not that easy to distinguish between a sine curve and a cosine curve. The only difference between them is a horizontal phase shift. Well, we've got one there. What is the horizontal phase shift in that function?
So you have to factor out the 2, or?
Yes, you do. In other words, the B needs to be in front of the parentheses. So,
Okay,
so what's left in there?
it would be would it just be 3, or I don't know.
Divide both of these terms by 2. When you're factoring out a 2, that's what you're doing. So when I divide this one by 2, I'm left with X. When I divide this one by 2, what do I have? What's 3 halves divided by 2?
3 halves divided by 2 would be
3/4.
3/4.
Check my math. 2 times 3/4 is 6/4, which is 3 halves.
Okay.
Now we have everything. The 2, stretch or compression?
Compression.
Correct. What's the 3/4?
Horizontal.
Shift by 3/4. And the +3?
Makes it go up 3.
Yeah, and L appears to satisfy most of those. I don't see the exact horizontal shift, but it's not going to be that easy to plug in a point here either. Only because, let's say we plugged in an x of, the easiest point to plug in is x of 3/4. When x is equal to 3/4, what is y equal to?
So 3/4. So 0, it's equal to 3.
No, what's the cosine of 0?
Oh, the cosine of 0 is 1.
Okay, so now we have the cosine of 0, which is 1, plus 3. So y should be equal to 4 when x is 3/4. Now we can find an x of 3/4 right about there and look exactly where y is equal to, 4.
Okay.
So L passes the check a point test. Notice why 3/4 was a better number to use, because we know what cosine of 0 is. If I put in x of 0, I don't really know what the cosine of minus 3/4 or minus 3/2 is. It's much harder to know that because that's in radians. Although it's still going to be 1. Oh no, it isn't. Excuse me. It would be 0. From the graph, when x is 0, y looks to be 3. All right, let's see. Let's move on. 46. What kind of curve is that? 46. What's it called?
I don't know.
Hyperbolic.
Hyperbolic.
And its basic function is this right here, which graphs like this. Okay, now the first thing you do when you graph a hyperbolic function is you figure out where its vertical asymptote and where its horizontal asymptote is. With the basic one, where is it?
The vertical asymptote
Is where?
Is at -3.
No, the basic one, this one here.
Oh, it's at 0.
Okay, where's the horizontal asymptote?
0.
Okay, so that's the first thing we're going to do whenever we graph any hyperbolic function, is to lay out the grid. Now in this one, I happen to know that that's what it looks like. It's asymptotic to both asymptotes. Okay, well now our function looks like y equals minus 2 over x plus 3 plus 1. Wow, what are we going to have to do to that? We're going to have to let me think for a moment. Why don't we write that like this? Now the minus 2 is what?
So -2.
What's the minus, first of all?
Flips it over the x-axis.
Yeah, so from my original picture, if I flip over the x-axis, I get this. Okay. What's the 2?
It's a compression.
Okay. What's the plus 3 in the denominator?
It's a vertical asymptote at -3.
Okay, so let's draw our grid. What's the horizontal asymptote?
One.
Yep. And normally I'd be drawing there and there, but this negative sign is going to should make it look like that and that. So that's what I'm looking for. Do we see that on there? C maybe?
Yeah.
No, the difference is C has a horizontal asymptote that's below the x-axis. And we know that that horizontal asymptote has to be shifted up 1. So let's find something else that looks a lot like C, only about a horizontal asymptote that's proper. P. P has the horizontal asymptote at 1, has the vertical asymptote at -3, and it's in the proper quadrants. Now, check a point.
So, do 0, it'd be -2/3 plus 1. So it'd be -1/3.
Positive 1.
Or 1/3, positive 1/3.
Okay, and P,
Yeah.
when I'm at 0, it looks exactly to be at 1/3. So P is a winner. You have to be a little careful plugging in points. As you saw on the sine curve, there were two graphs that were very, very similar, and the point came out to be the same. So plugging in just one point randomly chosen does not guarantee that you've picked the right curve. You know what I'm saying?
Yeah.
Okay. Let's see, we got 4 minutes here. Let's look at 40. Yeah, we've already done a hyperbolic function. Let's look at 49.
Okay.
These are actually really good problems. Okay, 49 is y equal e to the x plus 2 minus 3. Tell me what that is in f of x notation.
I don't know.
F of x plus 2 minus 3, like that. In other words, this is important that you be able to do this little exercise, because you always get it after it's been shifted, and you have to be able to figure out that it's that to know what kind of shift it is. So what is that plus 2 doing? What's the result of that?
It's moving it 2 to the left.
Horizontally, correct. And you know it's horizontal because it's inside the parentheses. Whereas this is outside the parentheses, so that has to be vertically down. So all we're looking for is the e to the x function that's been shifted left and down. A, maybe? A has been down 3. You need to pick a point for x. What's a good value to pick for x to see if A is proper?
-2.
Good, excellent. So when x is -2, what is f of x?
-3.
No. Remember, e to the 0 is 1.
-2.
-2. So when x is -2, y is -2. Bingo. A works perfect. Notice that I wouldn't really be able to tell by looking at this graph whether I was dealing with a shift. Yeah, I guess I would. you know that that's a shift left and down because the horizontal asymptote is now at -3. All right, we got through quite a few of those.
Yeah.
Yeah, the only ones we didn't do was a log one, but you know what the log function looks like.
Yeah.
The log function looks like this. And the key is this point right there. That point is 1, 0. Whereas with the e to the x, that point is 0, 1. The e to the x function is the inverse function of the natural log function. Notice that this is a reflection over the line y equal x, which makes it an inverse.
Okay.
Okay? All right, I will let you go. And the way let me stop this recording.